All right, so let's get into what acid-base chemistry is and the basics of it. And there's a reason, as you'll see, why we wait till after equilibrium to really get into acid-base chemistry. So acids, we don't say acids are things with a pH below 7. We have to get way beyond that kind of definition. So the basic definition is called the Bronsted-Lowry definition. Acids donate a proton in a chemical reaction. A proton, our symbol for a proton, if you look at what a hydrogen atom is, it's just a proton and one electron. If that electron leaves, what do I have? I have the H plus ion because my negative electron left. So H plus ion is a proton. So acids will donate the H plus ion from the acid to another substance in a chemical reaction. Let's look at this one. Here's hydrogen chloride. Let's write the chemical reaction. If I take hydrogen chloride gas and bubble it through water, let's look at what happens. Let's look at the Lewis structure of this. Here's hydrogen chloride gas. What is Lewis structure for water? So the proton's not just going to be hanging out in solution. What's going to happen to this? So this is the acid. Hydrochloric acid is going to be created. This H leaves, and what is that? A positive charge. That positive proton now leaves. It's not going to just stay anywhere. Remember, water is a very polar molecule. Here's my very electronegative oxygen. That's a negative charge that this proton is just going to latch onto. So the acid, hydrogen chloride gas in this case, is going to donate a proton. Water is going to accept that proton. What will I get in the end? So if I add an H plus to water, I get that. So the hydrogen is going to take one of these two pairs and latch onto it and be shared here. It was sharing this here with chlorine, but the proton itself leaves, and now it's going to come in and latch here. I now have an ion that's positively charged. What happens here? So this pair of electrons that hydrogen was sharing with chlorine is left behind, and now chlorine has it. So what do I have? I have the chloride ion. So HCl gas donated a proton to water, and that is what I have in the end. What is that? It's H3O plus. What is H3O plus? It's basically a water molecule that has added a proton. We have a special name for that one. It's a very important ion. It's called the hydronium ion. That will now be in solution. And what else do I have? The chloride ion in solution. That is hydrochloric acid. Well, if acids donate a proton in a chemical reaction, I got a little bit of room, bases accept a proton. So again, it's not about, okay, acids are pH below 7, bases are pH above 7. We'll get into some of that stuff, but our basic definition is in a chemical reaction, an acid is going to donate a proton, a base is whatever it is that accepted the proton. In this case, water is acting like a base. Why? Because it's accepting a proton. Now, water is not a base. It is a neutral. If you have pure water, the pH is 7. It's neutral. But in a chemical reaction, it can act as a base, which just means it can, because of this electronegative oxygen and the polar nature of water, it can accept a proton and act as a base in a chemical reaction. So the hydrogen chloride gas is acting as the acid. The water molecule, in this case, is acting as a base, and that's what I get. That's an acid-base reaction. Let's look at another one. if I have a solution, this thing is called nitric acid. So HNO2, it's not HNO3, which is a strong acid. We'll get into this one. H2O liquid. Difference here in the last one. The last one, every single hydrogen chloride gas will donate a proton to water. There's no more hydrogen chloride gas in that solution. In this case, if I have this molecule in solution, what's going to happen? Some of them will donate a proton to water. Add a proton to water, what I have? H3O plus ion. That is the acid ion. That's the thing when we're measuring pH, we're going to look for the concentration of this. So let's give it its name. It is the hydronium ion. It is a water molecule that has accepted a proton. Here's my hydronium ion. What's left? If I lose H and a positive charge, NO2 minus. That is the nitrite ion in solution. So here is the reaction. What has happened? This has acted as the acid. Water, again, acted as a base. Water is not a base, but it can act like a base. We'll be using that terminology a lot. And here are my products. Now, in this case, the first one was not 100% that way, no reverse reaction. For this acid, and for most acids, there is a reverse reaction. What is the reverse reaction? That proton that got donated back that got donated to water goes right back. It's the reverse reaction. So in this case, not all of this will have gone and formed that. So then what happens sometimes, that hydronium ion will donate the proton right back. In the reverse reaction, this is acting as an acid, the hydronium ion, and this nitrite ion is going to act as the base. And it goes back, right? H plus. But we want to use a term when we're talking about, is it acting as an acid in the forward direction or in the reverse? So what we have is, if it's acting as an acid in the reverse direction, we call it the conjugate acid. If it's acting as a base in the reverse direction, we call it the conjugate base. So acids donate protons, bases are accepting a proton in this reaction. And if it's in the reverse, we just say conjugate acid, conjugate base. So most acid-base reactions are equilibrium situations. What about, so we keep saying water is a base. Can water actually, but it's neutral, it's not a base. Can it act as an acid? Yes. Here is an example. A solution of ammonia in water. This is another equilibrium situation. Ammonia, because of this arrangement, look what bases need. In order to be a base, you got to have a pretty electronegative atom and an unshared pair. Why? Because if it's going to accept a proton, boom, I got to have somewhere negatively charged it's going to grab onto. So what's going to happen? One of these hydrogens, one of these protons is going to pop off, and it's going to latch on right there. I then have, now the nitrogen is surrounded by 4 hydrogens. So we generally call the OH, or the hydroxide ion, the base. Notice hydronium ion is a water molecule that has accepted a proton. What is hydroxide? It is a water molecule after it has donated a proton. So look what's happening. Water is donating the proton. In this case, water is acting as an acid. Ammonia is acting as a base. This reaction is an equilibrium situation. There is a reverse reaction. That proton goes right back. Going from this, the ammonium ion, this is going to act as the conjugate acid. Hydroxide is going to be the conjugate base. So with these introductory reactions, some of them are equilibrium. The first example with the hydrogen chloride gas, 100%. We're going to develop these terms, strong acid, weak acid, but this is basically what we're going to be working with, and of course adding equilibrium constants to this and continuing to go, learning how to calculate pH and that kind of thing. So here's our introduction. Much more to come on acid-base chemistry.